Physical AI is all the rage these days, but designing for a system is not something you want to do from scratch.
That's
Could you
right.
tell us briefly what we're going to be seeing here?
So today I'm going to be talking about the Cadence Physical AI Chiplet Platform. It is a collection of 3 chiplets, a CPU chiplet, an AI chiplet, and a system chiplet that together, package level scaled, will deliver a high-performance edge AI solution.
Perfect, let's take a look at it.
So just so we're clear, physical AI systems include automotive ADAS, drones, robotics, aerospace and defense. And these applications all have very similar use cases. They all need some type of AI acceleration. They typically require CPU execution, and they require some sort of system interfaces. So I'd like to introduce the Cadence Physical AI Chiplet Platform. It is a 3+1 chiplet platform that consists of a CPU chiplet, an AI chiplet utilizing Cadence's Neo NPU AI, an optional domain specific, this would be an add-on to the system, and today's demonstration will be the base system chiplet. This is the primary chiplet within this system that facilitates the communication across chiplets and also includes the interfaces to things like memory as well as standard interfaces such as PCIe. Today's demonstration is the system chiplet prototype. It includes dual UCIe 32 gigabit interfaces, an interface to LPDDR5X 9600 memory. It utilizes the Cadence network on chip, but it also integrates the Cadence chiplet framework. The Cadence chiplet framework manages the interaction between the multiple chiplets, including system boot, system communication, debug, and all types of clocking and resets. The demonstration, here is our actual silicon. The silicon has 5 die packaged inside of it. These are all identical die, configured in different fashions so we can test between primary and secondary chiplet operations. 2 die are linked via a 7mm UCIe link, and 2 die are linked by a 25mm organic substrate link. These execute at 32 gigabit across UCIe standard. Our demonstration is going to show interfaces to the LPDDR memory. We're going to show bandwidth across the 7mm and the 25mm UCIe links. And then finally, we're going to show some edge AI using SqueezeNet, which is a very compact edge AI software. So the first demonstration we're going to do is LPDDR5X memory operating at 9600 within our system chiplet. And we can select to do read writes, and as we execute, we can now see that our embedded DMA is reading and writing from embedded SRAM into the LPDDR5X memory operating at 9600, and we're achieving around 21 gigatransactions per second, which is slightly lower than the theoretical maximum, and that's just because we have write and read interleaving disabled. But now what we're showing is our internal DMA is activating our embedded SRAM and writing into and reading from LPDDR at 9600 gigatransactions per second. So the next demonstration we're going to show is we're going to utilize the 2 UCIe interfaces running at 32 gigabit, and we're going to do read and write across both of them. So let's execute that. Now you can see that our embedded DMA is reading from the SRAM and writing, and we're going across dual interfaces, and we're achieving around 92 gigatransactions per second, slightly below the theoretical maximum, which is only bandwidth limited by our SRAM. So finally, we're going to demonstrate some edge AI. We're running the SqueezeNet Convoluted Neural Network, CNN, which is a highly optimized edge AI CNN. We're going to send an image across the UART interface and have it processed. This is just running on a very small M7 ARM processor. This chiplet was not designed specifically for Edge AI. It has no AI accelerator, but we can still show the power of a chiplet within this system. So we'll send our image, it processes and returns rhinoceros beetle.
That was a great demo. How are people going to get involved with this, and how can they enhance the system that you have as a base?
So we support additional domain-specific chiplets, so you can add your specific intellectual property to this system. We support open standards, such as ARM chiplet system architecture and the OCP Foundation chiplet system architecture. That means you can build either your own interoperable chiplet, or you can have Cadence design that for you, integrating your IP. Overall, we can accelerate that time to market by utilizing our chiplet framework that automates many of the steps of chiplets. And in turn, that reduces the NRE because we're reusing work that we've already developed.
Are there any other considerations in terms of the design or the complexity that Cadence enhances with your tool set?
We have a tool called SoC Cockpit that we utilize to automate our whole flow. So we can utilize that again to enhance the overall creation of a chiplet. It builds in our intellectual property, encapsulates it for chiplet usage, and accelerates that whole design flow.
Excellent. Well, thanks for filling us in on Cadence's tools and a way to get into physical AI a lot quicker.
Yeah, thanks, Bill.